Good evening all. Welcome to the last session of this particular course, Optimization from Fundamentals. So, to kind of give you a brief review of where we started out with discussing of sequences and how do we determine the existence of a particular solution in case of optimization problems. And then once we know that we know a solution can exist, then we moved on to a oh sorry, I think I'm sharing a wrong screen. Just give me a second. Share my screen. Yeah, I think now you can see my screen. Yeah. So in the first week, we started out with discussing on what exactly is an optimization. Is essentially we have a certain problem where we have different alternatives and we need to find the best alternative out of them. And we started out with saying how do we mathematically formulate this, and then we understood that okay, we move in a sequence. We start with some iteration, and then we keep moving it till the iteration reaches the that particular state that we want to reach it. Right, like we start from some point, and then we keep on improving it till we reach a state where no further improvement is possible. And when that state achieves, we say that it is what optimization is. This is the same strategy that have been used throughout the other methods as well, even in inferior point methods or cutting plane method or anything that we have discussed after that, Lagrange multipliers or any update that we do, we start from somewhere and keep improving the point till no further changes are observed. This is the same thing that has been used throughout the course. And then we discussed some theorems on this particular optimization. So where we have seen that as long as we have a bounded sequence, as in at every iteration, if the values of your decision variables are bounded, then that series is definitely going to have a convergence subsequence. And we also seen Weierstrass theorem where we need some conditions on our objective functions. The function needs to be a continuous function. The feasible domain has to be closed and bounded. And these are the problems which we see every time in engineering problems. In all the engineering problems, we come up with an objective function which is more or less a continuous function. And in that scenario, whenever the domain is a feasible region is bounded, closed and bounded, we need to ensure that it's closed and bounded. Then we know for sure that the solution exists. And once we know the solution exists, then we understood what okay if a solution exists, and we kind of labeled the different kinds of solutions from them. We use the Weierstrass theorem, and then we define different minimas: local minima, global minima, unconstrained, strict, local, isolated, different kinds of minimas. Essentially, the idea is to see that in the neighborhood of that particular point, that has to be the minimum value that is possible. That is what we are trying to find. Depending on what the size of neighborhood, we have all these different kinds of local minimas. And then we discussed on some of the notations that we will be using throughout the course, which are kind of not important right now. And then we discussed what is the Taylor's theorem, and from the Taylor's theorem, which we come up with the first order sufficient condition, which says that whenever a minima happens, then the gradient of the function should be 0 at that particular point. And then we told that okay, this is not a necessary condition, and then comes the second order condition, which says that for a minima to occur, the Hessian or the second order derivative should be a positive semi-definite matrix when you have a vector, or in general it can be if you have a single variable, then this has to be strictly greater than 0. That is a condition that we kind of came up with. So, but this is for a scenario only when you have X star belongs to S where this S is an open set. That is how that is a major limitation of this particular criteria. So the moment we have closed domains, like in feasible region is kind of bounded, like the polygons or whatever things that we have drawn letterwards. Like when constraints come into picture, these conditions do not directly apply. So we have to modify these constraints to account for those. So we have to modify these conditions to account for the constraints. So then we discussed on the implicit function theorem, which exactly does that. So we have an open set. So implicit function theorem converts the constraints into a new problem, where in the new problem, the domain becomes an open set, so that we can use the first order and second order sufficient conditions. We also discussed something on least square regression for curve fitting, where you have certain parameters, you have a model for it, and then you try to minimize this function. Depending on the type of this norm, you have different kinds of regression. You can minimize square, you can take absolute, cube, and all of that. And each one will have a different kind of impact on the accuracy, and depending on the data set you have. Then we discussed that okay, whenever we have constraints, this implicit function theorem is useful but it may not all, we cannot always convert the problem into a single variable. Like for example, when you have a two variable problem and it is bounded, all we are doing is converting it into a single variable problem, in a single variable unconstrained problem, and then solving it. This is not always possible. So we thought, okay, some kind of a better way to do it is where the Lagrange multipliers come into picture. So we define the same thing as before, but then we define in terms of some Lagrange multipliers, and then we say we try to minimize the same function plus lambda times whatever conditions I have. So if f0 is my function that I'm trying to minimize or maximize, so I'll try to maximize that plus these terms and then take derivative with respect to x and then make that equal to 0. So this kind of what it does is essentially take the original problem and all these Lagrange multiply will be the extra constraints that I'm adding. So then the number of equations and number of variables will become equal. So then I can solve them normally. In general optimization problem, both of them are not equal. That's where the problem comes. But once we add the Lagrange multipliers, this becomes equal, and this is possible only when you have all the constraints as equality constraints. If you have inequality constraints, then this particular thing cannot be done, and then we'll have other problems. So with this Lagrange multipliers, again the same conditions satisfied. So for the Lagrange function, we need to have the first derivative to be 0 and the Hessian to be, for a minimization, Hessian to be positive definite. For a maximization, it should be less than or equal to 0. And the physical meaning of this Lagrange multiplier is it tells us how sensitive is the final objective value with respect to each of the constraint variables. That is what the physical meaning of Lagrange multipliers is. But as we see that all these derivations are only for equality constraints. So then we discussed on different kinds of transformations. So how can one transformation can actually be used? The same optimization problem, the same solution can be reached by using a different set of ways. So we discussed different kinds of transformations, as scalar multiplication will not change anything. A one-to-one mapping of the domain will kind of does not change the feasible domain, but the objective function may change. A monotone transformation is where you take a constant, a function that is continuously increasing or decreasing, and use that function to transform your objective and constraint variables. And then we also discuss something important, slack variables. This is something we will discuss today as well. These are the variables which are like whenever you have an inequality constraint, we use these variables to convert them into an equality constraint. So when you have an inequality constraint, all we try to do is we add an extra variable si to make it an equality constraint. So once it is an equality constraint, then we know how to solve it. Solving them is a little straightforward compared to the inequality constraints. So, and then we also have seen linear equality constraints. Whenever we have equality constraints, then we can always rearrange the variables and then reduce the number of variables in my original objective function. For example, if I have two variables in my objective function and I have one constraint in terms of x and y, for example, then I can always write y as a function of x and then substitute it back to reduce the number of variables in my original optimization problem. This is very similar to your implicit function theory. Then came the very important concept in the entire course is the convex analysis, where we discussed on what exactly is a convex set and why is it important. So because we know that if it is convex, the main definition says that if you have 2 points on that particular set, then any linear combination of the point will also belong to that particular set, and that is what we call an convex set. We have different theorems on this. We define what a half space is, what a polyhedron is, and all these polyhedron, these are the different definitions. I'm not going through the definitions, but the main idea here is all these things are all these are convex sets. And why do we need convex sets? It's because we have some important properties of these convex sets. One, the most important property is you can always use these polyhedrons which are convex. And once you know you have any set, you can always use a convex or something and get a polyhedron out of it. And once you have a polyhedron, we can know that for a convex set, we have some extreme points. And the way to represent the set is by using these extreme points and extreme rays. So a convex set can be represented in a different way. So the main idea, that the main takeaway from this is whenever we have constraints, some physical constraints which cannot always be written in some way, first we convert them into a convex set, and once it is converted into a convex set, then we know that this convex set can be decomposed into extreme points and rays, and optimal points are going to lie on these extreme points only. That is the main takeaway from this. So for convex sets, once we find these extreme points somehow, then all we need to do is search only these extreme points instead of searching everywhere else. So that kind of simplifies the problem. So this basically means Minkowski-Weyl theorem only tells us that you can decompose the entire convex set into a set of extreme points as well as rays. Then we discuss what is a standard form of a linear programming problem, and this is where we use the concept of extreme points and told that the solution will lie in one of the extreme points. The next one is the most important concept. The other one is the separating hyperplane theorem and the duality theorems. So we told that we have a basic feasible solution, which are the solutions at these extreme points. And then we discussed something on separating hyperplane theorem, from which we kind of came to a conclusion that the same problem can actually be posed in a different way. So one problem will be in terms of our decision variables, and the other one will be in terms of the constraints that we are having. That is a dual problem. In the primal problem, if our decision variable is x and the constraints are b, then in my dual problem, these will be reversed. So this is my primal problem, and in the dual problem, I will have the constraints as variables. So whatever is the constraint here, that will go as a variable here, and the variables will become the constraints here. So the objective will come in the constraint part, and this constraint will go into the objective part. So that is a primal dual thing, and then we discuss something called the weak duality and strong duality. Eventually, the conclusion is once you have a strong duality in place, whatever the solution of primal and dual will actually converge to the same point. That is the main takeaway from this. Then we discuss the most important one out of all the week 7 lectures is the complementary slackness condition, which says that whenever you have a constraint and the corresponding variable in the dual space, the product of them should be zero. That is, if one of them is a finite value, the other one has to become zero. That is the most important criteria. And why is this important is because when we are solving over all the extreme points in the dual space or primal space, the combined dual plus primal space, we have to reduce these things. We will see this in today's today problem also, how this complementary slackness is useful in kind of reducing the search space. Then we discussed something called a tangent cones. So previously we told that, okay, once we get an extreme point, we can find a solution. But then this is another way to see it is, so once I have a convex set, the tangent cones are essentially the directions which tell me how to approach the points which are an extreme. So especially when you have an closed set or a bounded set, when your feasible region is a bounded set instead of an open set, then I cannot directly use the previous conditions like gradient equal to 0 or Hessian to be positive. So I need to come up with a new additional conditions. So the minimum can happen at the boundary or it can happen outside the boundary as well. So then I need to solve the problem in such a way that I identify boundary in some way, and tangent cones are one way to do that. So these are essentially what the bottom line is. These tangent cones will help us to identify these points. The point where I have to search for the condition where the gradient is 0. This essentially it will reduce the number of search points that I am doing. Then from this tangent cones, we came up with an interesting concept of active constraint. It says that out of all the constraints in the problem, whenever you have that particular g, or whenever you have an inequality constraint, then you have to search for the entire region where g of x is less than or equal to 0. But then you have to search only for those c's where it will be exactly equal to 0. Those are called the active constraints. Whenever it becomes an equality and equality, then it becomes like a normal problem with equality constraints, and then I have the number of equations, number of unknowns to be equal, and then I can solve the problem. But then we understood the challenge with this is the way we define this particular criteria to be equal to 0 or something will require us for the determine tangent cones also. But then identifying a tangent cone for a given set, like when you can physically, when you can visually draw it and graph it, then it would be easy. But if you cannot draw it, for example, if I have a 5-dimensional or say 10-dimensional problem, we cannot always draw it to identify the tangent cones. Then we need to come up with a different way to how to write this g of x in the first place. There could be 100 different ways to represent the same region. You can represent the same region using multiple ways. So how do we choose which way is the right way to do that? Then comes the constraint qualification theorems, which says that you choose the way in which the gradients of this g are linearly independent. That is one that is one kind of constraint. And once we know that the constraint qualification holds, which means our tangent codes can be identified, then we can use our same condition that we derived previously, that is the gradient to be 0, but then the gradient should be taken for the Lagrange function instead of the objective function. That's the only difference here. But these are only for your equality constraints. The moment I have inequality constraints, then I have to use something called KKT conditions, Karish-Kumfikar conditions, where the only change that we have to do is we have to add an extra thing where you consider only the active constraints, and then you also have the complementary slackness condition. So for all the active constraints, they will become equality constraints. So this remains the same. This is just like your Lagrange function. But then for other inequalities where your where for inactive constraints, you need to have the complementary slackness condition. So which means the lambda will be equal to 0. And for wherever for active constraint, g will be 0 and lambda will be a finite quantity. So in addition to this, we need to have this extra complementary slackness condition, and that's where our KKT conditions will be. Those are our KKT conditions. And the most important one later is a convex function. This is the same thing that you most often encounter. And once you have a convex function, the main criteria to identify that is your Hessian is going to be a positive definite one. So Hessian is going to be greater than 0. That means it is a convex function. It's like a quadratic function, and once a global and the minima for a convex function will be the global minima. So if you have a convex function and if you found some minima using any technique, then that is a global minima that is going to happen for that particular function in that domain. Then we discussed on other kinds of constraint qualification theorems. These are more this week most of the discussions are on the theoretical ones on how you derive the strong duality for convex optimizations. So the main takeaway from this particular week is you understand that when you have a convex function subjected to convex constraints, then eventually you will have a solution for it. The minima will be a global minima. That is the only conclusion that we came up to this in this particular week. And then we once we are done with the convex optimization, we know that a minimum exists and we know that we can find it. But then all of those methods are kind of telling us that okay, a solution exists, but they do not tell us how to reach the solution. So in week 10 onwards, we started out with methods that will actually help us to reach the solution. So we start with some point and then we know how to move from one point to the other point. We discussed several methods. One is the line search, gradient descent, Newton methods. All these are different methods which will work only for, again, all these methods are for unconstrained optimization. In unconstrained optimization method, okay, we start with some iteration and how do we improve it? So for the improvement, the idea is in any of these lines as or any of this, you take the gradient and the gradient will be in such a way that the function value will increase. So you try to move in a direction away from the gradient. But the question that remains is how much to move, how far to move, and how accurate is the local approximation of the gradient that I'm taking. These two are the main questions that we need to use, and depending on them, we have different methods. Simple line search, we just start with some point and then we keep updating the points till we discuss all old conditions, which says that okay, how these are kind of telling us okay how I will move in certain direction, but how far I will move is essentially move till your value is decreasing, till the objective function value decreases, and that is where you choose the alpha value, and then sorry, you will choose the alpha value, and once you get the alpha value, you keep increasing the value of xk in that direction. Pk is basically your gradient, some function of a gradient. Which function to choose, again, that is where the other methods will come. I can use either Newton method or I can use a gradient descent method. In a gradient descent method, I'll just take something like this for my pk. Pk is minus grad f and b and stop there. But we know that once we use this method, then there are chances that it can oscillate. The gradient can become 0 in some region, so it will be very slow. So near the optimal, as you go closer and closer to the optimal point, this gradient will become will become very close to 0. So your each and every update step will actually become very close to 0, and then you might not actually reach faster. So you might come up with you have to come up with other methods that will increase your rate of convergence near the optimal point, and that's where Newton method comes. So in addition to gradient, it uses the second order Hessian also. So once both of these are taken into account, then the rate of convergence is much faster. But then the challenge is this method works only very close to the solution. If you're far away from your solution, if your initial guess is very far from the solution, then it cannot actually give us any, it may or may not actually converge. But then again, the challenge here is calculating Hessian itself might be difficult in some problems whenever you have some very complicated functions, complicated objective functions. And then we told something called a quasi-Newton method, where you approximate this Hessian by again taking a finite difference of your grad f. So you calculate grad f and you take finite difference to get the second order derivative. But all those above methods are for unconstrained optimization problems. Then comes the constrained optimization problems. So how do we convert the unconstrained? How do we convert from constrained to unconstrained? Is by adding something called a penalty function. What this penalty function does is, if the particular point is satisfying the constraint, then this penalty will be 0. The moment it is not satisfying, it gives more penalty. Just like as the name sounds, it's like you violate some traffic rule, then you add a penalty for it. If the penalty is too much, then the chances that the person will violate that particular traffic rule will be very less. In a similar way, this penalty function also does it. But then the challenge here is how much penalty to keep. So how much fine should I keep for crossing the for kind of breaking the signal or breaking the line or something, some traffic rule? How much fine should I say, for example, if you don't wear a helmet, how much fine should I keep? If you cross a red light, how much fine should I keep? So how do I determine what to keep? And that's where we have to keep on iterating different values And it turns out that in most of the optimization problems, if the penalty function is say quadratic or something, that is in the next week lectures, where we understood that okay, if I choose a quadratic kind of thing, the amount of penalty that I have to keep to in order to get the solution that I want is close to infinite, which is not practically possible to do. Hence, we came up with some other strategies called an augmented Lagrange method, wherein we can keep a finite penalty value and still get to the ideal solution that I want. So it's like keeping as small amount of fine as possible and still reaching the optimal solution that I would want to. So like people will still follow the traffic rules without actually paying so much fine. Still, you will keep a finite value of fine, but still people were able to reach that. And how do we do that trick is actually using the concept of both like augmented Lagrange, where you have the penalty function. In addition, you also have the normal Lagrangian term. So this way, all we have to do is adjust this penalty such that our constraint is actually the constraint can actually be satisfied by adjusting your theta value or your Lagrange parameter value, so that your h of x will be 0 instead of making ck tends to infinite. Then we discussed something called cutting plane method, which essentially says that when you have a nonlinear problem, you can always convert it into a linear problem by taking a subset of it and by taking an outer approximation of it using a polyhedron, and then solve that particular problem. And you keep solving it till you reach the solution, whatever. If that particular solution for the sub problem is inside the feasible domain, then the problem is ended. If it doesn't reason, again you can outer approximate it using this particular relation to get the solution. But then the challenge with all these methods is once you have, even if you make a linear problem, all you have to do is again, you have to check all the basic physical solutions. So you have to iterate over all the extreme points and then determine what the best one is. So instead of going over the extreme points, interior point method, what it does is it directly goes through the interior of the domain by bypassing instead of oscillating from edge to edge, it goes directly through the interior point. And how does it do that? It because essentially by using both the primal and dual space. It uses both the primal equations like ax minus b, and it also uses the dual space equations, and then it also includes the complementary slackness condition. So by solving all of them together, it knows how much to, instead of going from point to point, it directly goes to the interior of the domain to finally reach the solution. All of these problems, the thing we discussed on what for constrained as well as unconstrained problems and different linear, non-linear problems. Even for non-linear problems, you can convert into linear and then solve it. But then in all of these problems, each of your variable is kind of a fixed value. But then in the last week of the lectures, we discussed something called a dynamic optimization problem, wherein one step will actually be if you choose a particular decision at a particular point in time, that actually affects your future decisions. So then the problem becomes more combinatorial. And then it increases the complexity of it. So in order to reduce that, we discuss something called instead of trying to determine what the action value is, we try to get up a strategy or a policy where you try to determine the optimal action as a function of the state at that particular point in time by trying to minimize this particular function. But then we discuss the principle of optimality, which says that if you are already on an optimal path from say point A to point B, and if some particular point C also lies on it, then that C will be the optimal point. So instead of going from front to back, you actually go from the last step to the first step. That is the dynamic programming equation. So you start with the last step and you go backwards till you reach the first solution. And that's where the Riccati equations also comes. This is for a very special scenario where you have a linear transition dynamics. So xk plus 1 is given by this linear equation, and then you also have a quadratic cost function. Only in this special scenario, we have the special case of ulk, all these values. And then once we have the optimal actions, we can always calculate the total optimal cost at the initial state as a function of this. I think there is a mistake in this. I've updated in the yesterday slides as well. This is 0 to n minus 1. Because for the nth step, we are not taking any action. So from k equal to 0 to n minus 1, whatever steps you take, you have. And for the last step, you do not take any action. So that will not come here. Okay. So we started out with existence, and then we understood, okay, constrained, unconstrained, and we started out with unconstrained. We solved the problem as unconstrained. Then we took a constrained problem, and then we understood the methods, how to convert a constraint to an unconstrained problem, and then use the unconstrained methods. And we also saw, okay, instead of converting it into an unconstrained, how can we solve constrained problems directly also? And then we finally discussed on dynamic programming methods. So these are the kind of main things that we discussed over these weeks, but we haven't solved any problems on them. So now I have some problems, or maybe I'll just So before solving the problems, are there any other any questions up until now in the overall thing? Okay, then we'll solve some problems. I'll just show you how some of these problems can be solved. So the first one here is, say you have a factory making chairs and tables. Say you're owning a factory and you can sell one chair and get 1600 rupees. You can sell a table and get 900 rupees. So let's say chair as x1, table as x2. But so obviously, like you have some physical constraints. So you have certain amount of wood. You have 300 kg of wood. So this is what you have as your supply. And you know that you have to use 30 kg for making one chair and 18 kg for making one table. So to put it mathematically, 30 times x1 is the amount of wood used for making a chair, and 18 times x2 is the wood used for making a table, and this should be less than or equal to 300 kilograms. And the other type of constraint that you have is the amount of labor force. These are usually the type of constraints you have. One is a material constraint, and the other one is labor constraint or manpower constraint. These are the usual type of constraints you found in these problems. So the other one says that, okay, you can make a table, but you require 20 hours of 20 man hours, and table can be made in 8 hours, chair can be made in 20 man hours, and you have availability of only 160 man hours. So these are the constraints I have. And I know I have to produce something, otherwise I'll be out of business. So x1, x2 should be greater than 0. Ideally, I don't even want this equal to 0. I want it to be strictly greater than 0, but in this problem, we'll just take greater than equal to 0. So our objective is to maximize this profit so that these constraints are satisfied. So two things. First, this is a maximization problem. Second, it is a constraint problem, and these are inequality constraints. So you can solve it in different ways. We have discussed several methods. So how do we approach it? So the first one we can try with, say, KKT conditions. Kuntakar, or basically these are my KKT conditions. So first step, I have to write my Lagrange and then try to minimize the Lagrange function. So how do I write my Lagrange? So this is a maximization problem. So I'm multiplying with minus so that I'll convert this maximization into a minimization. So then I can minimize this function. So everything, whatever we discussed in the lecture, will be consistent with that. So I'm taking minus 1600 x1 minus 900 x2. Instead of lambda, I'm putting u. So these are my Lagrange multipliers. Yeah, since we need maximum profit, we are putting maximize here. But in our notation, we are using del x del all. Always our Lagrange is a minimization. So I just multiplied with minus. So minimizing a negative quantity is same as maximizing the positive quantity, right? So this is the transformation that we talked about. Both are the same kind of object optimization problems. Like minimizing y is equivalent to maximizing minus y, or minimizing minus y is equivalent to maximizing y. The extra thing that we are trying to do here is these particular two terms. So when you write your Lagrange function, it has to be function of x and your new constraint variables u1 and u2. So these are the Lagrange multipliers where you write u1 times whatever constraint you have and u2 times the second constraint. So this is my Lagrange. We know that the gradient of Lagrange with respect to x should be 0 as one condition. And the second most important one is the complementary slackness conditions. Yes, is minus u1 times the constraint and minus u2 times the second constraint. And the next one is the complementary slackness, which is like when we said that lambda times s should be 0. So u times the first constraint should be 0 and u2 times this should be 0. So this again, as we discussed before, is this particular any of these constraints can be active or inactive. If the constraint is active, then this particular value will be 0 and u1 will be some positive quantity. And if, for example, this constraint is inactive, then u1 will be 0. If you have u1 equal to 0, then that particular constraint will be equal to inactive. If u1 is a positive quantity, then that constraint is an active constraint. So, but how do I know which value to choose? So first we write down the equations. So we know that gradient of L should be 0. So I take del L del x1 and del L del x2 equal to 0. So now I have two equations here and I have two unknowns, u1 in terms of u1 and u2. So I can solve these equations and get the values of u1 and u2. Once I solve the equations, let's see, these are the values I'm getting. So now comes the important point. So since u1 and u2 that I got here are positive, which is exactly what I want. So if this particular constraint is satisfied, then and I have both of these to be positive, now I can substitute them in 2 and 3. Since u1 is a positive quantity, there is no other way. This particular term has to be 0. Since u2 is also some finite quantity, this particular equation has to be 0. So those will be my next equations. So I have 4 equations and 4 unknowns. Now I have solved all of them. I can solve this to get the values of x1 and x2, and those are the optimal values. And we know that if the KKT conditions are satisfied, then that is the minimum value that can occur for the particular objective function. Now imagine a scenario, for example, if it turns out that this u1 is negative, say if you got u1 to be minus 2 or something, it didn't happen here, but let's say you got u1 to be minus 5 or something, then what you will do is if u1 is minus 5 or something, or maybe there is another problem where you will encounter such a situation. But what will you do? If u1 is negative, then what will I do? I solve this equation and let's say I got u1 as negative, but my KKT says that both have to be greater than or equal to 0. So what will I do then? As in, so what will you change? Any example? How will you change? Any idea you have? Okay, so if one way you can do is if this turns out to be negative, then you can directly make it equal to 0, make u1 equal to 0 and use this equation directly. If u1 equal to 0, then this equation is not true. Then it becomes, I'll show you a problem where this u1 is actually negative. That also will solve. But the other way you suggested is okay, we'll not use this method at all, we'll use a different method. So what other method can I use? Let's say I will use the Lagrange multiplier method with slack variables. Slack variables is also one kind of transformation, right? So I can use that. So I have my inequality constraint. So I have 30x1 plus 18x2 less than or equal to 300. I'll add a slack variable plus s1 and say s1 greater than or equal to 0. This could be one way. Once I add a slack variable, it becomes an equality constraint. So once I have equality constraints, I can put the Lagrange multiplier and formulate a problem like this and make del L del x1 del L del x2 equal to 0. Solve for lambda 1, lambda 2 and stuff like that. I can do this. Do you see any problem in this approach? But is there any problem with this approach? It takes time, okay. But then any other problem? Like, did I miss any equation? I wrote these equations, but did I miss anything else in this equation? I haven't explicitly written this anywhere, right? Whenever I add a slack variable, I need to ensure that s1 greater than or equal to 0. But in this Lagrange equation, I didn't write anywhere that s1 should be greater than or equal to 0, right? So this won't physically represent the same problem. So it will be, so I have to do something that will ensure that s1 is greater than or equal to 0. That is not enforced here. So you cannot directly use this. Even if you try to solve for it, you'll end up with equations that you cannot solve eventually. So to ensure that, the strategy is to use, instead of s1, you put s1 square and s2 square. Now you know s1 square is always positive, so this is always true. Then if you solve, what will happen is you will end up with the complementary slackness condition again. So you will come up with lambda 1 s1 equal to 0, lambda 2 s2 equal to 0. So again, if you do even with this method, you will again end up with the same equations as you started out with using KKT conditions. So you will get the same equations as this. So whichever method you use, you have to solve that because there is no advantage you are getting in any way. So the problem is the same problem. It's just in a different way. These are just different transformations. So eventually you're going to solve the same set of equations and get the same thing. It's a method. Yes. Y. Where is Y? Yeah. So Y is basically 1600 x1 plus 900 x2, right? I have used. Yes. Yeah, that is another important point. So once you find this, you have to find Y. That is a critical thing. Like I've solved for X everywhere, and once I solve for X is when I substitute for Y. Once I found the X values, I'll substitute it in that Y equation and get the optimal value of Y. So this is important. This is our objective. We don't care about this at this point. Okay, this problem is clear. Okay. This is another problem. This is also very similar. You have the same kind of problem. You try to maximize the profit. So you can go through the question. I'll upload this in the same drive folder. So essentially you have a refining plant where you have two different types of products you can make. Each one has a different profit and each one has a different transportation cost. So essentially each one has a different cost price and selling price. So eventually you have to determine how much you have to, how much of it, how much of type 1 you have to produce and how much of type 2 you have to produce so that you will have the maximum profit. That is the problem. Subjected to the different constraints on the amount of transportation you can do, the amount of so depending on the packaging facilities and depending on the other constraints with respect to the raw material. Based on the raw material as well as based on the packaging cost, you have certain limitations. So these are my constraints. These are the packaging constraints. So I cannot have x1 greater than 210 and x2 greater than 230. Now I have, it's the same set of equations. You're trying to maximize the same function, but then I have four inequalities now. I have two variables and four inequalities. So if I write the KKT conditions, then it will get more and more problematic. So it will have, this is my objective function. These are my four other conditions. And each condition will have a complementary slackness which says u1 times is equal to 0, u2 times is equal to 0, u3 times, those are the other equations I'll be having. So these are all the equations I'm having. So these are four equations and I have two equations. So here I have two equations and the complementary slackness will give me four equations. So I have six equations and I have one, two, six unknowns. So I have six equations and six unknowns that I have to solve for. The only challenge here is these equations are linear. These two equations are linear, so this is not problematic. But the other four equations, these four equations are non-linear. So solving them is a little tedious one, but there is no option. We have to solve them in some way and to get the solution. So this is a brute force way I have shown here. Now you have all the tools like MATLAB or something where you can just put these equations and it will give you the solution. But then if you are doing with the hand calculation or something, then you have to try all possible combinations. For example, if you take this equation, equation 4, it has two different states. So you can either take u1 equal to 0 or you can take the entire expression to be equal to 0. Now you have to see, okay, let's say u1 equal to 0 and then go into the next equation. Here also you have two different causes. So u1 can be 0 or not 0. Again, for this particular combination, again I have to check for u2 whether it is equal to 0 or it's not equal to 0. Then you have different, all those combinations you have to keep trying till you reach your till uh, till you reach all these conditions, all these equations 2, 3, 4, 5, 6, 7. Till all the six equations are satisfied, you have to keep repeating. So what I have done is I've taken two equations at a time. Take 4 and 5. Then if I take 4 and 5, then I just have two equations like 4500 minus 10x1 minus 16x2 equal to 0 and 2500 minus 9x1 minus 7x2 equal to 0. These are two equations and two variables. So I can directly solve them and get x1 and x2. So I got x1 and x2. Once I got x1 and x2, I can calculate the values u1, u2 and other values. So it turns out that u is negative. So this should not be happen because our constraint is violated. So this A does not satisfy the KKT condition. Now I took a different combination, 4 and 6. With that, I got all u's to be positive, but then the equation 5 turns out to be negative. So that is also not satisfied. Again, I took a different combination, 4 and 7. If you see 4 and 7, here I directly get x1 equal to 210. Sorry, 4 and 7. 7 is this equation. So I directly get x2 equal to 230. So I'll substitute x2 equal to 230 and 4 in this equation. If I substitute x2 equal to 230, I can get the value of x1 and I'll check all the values of u's. Then I got u to be minus 2 or 6, which is again negative. So this is also not happening. So because of this is also not true. Because of this is not true. Again, you keep doing that, you'll have something or the other getting negative and PKT conditions are not satisfied. Only this combination 5 and 6 will actually give you a correct solution. So when you take 5 and 6 together, which means your u1 is 0, which is an inactive constraint now. u1 is an inactive constraint and your u4 is 0 and remaining everything is positive. So this combination actually give me all the KKT conditions to be satisfied. And then I'll get the objective value. Yes. Mhm. Hmm. Okay, when I write 4 5, what I meant is for example, if you take 4 and 5 here, either u1 can be 0 or the term in the bracket can be 0. So when I write 4, I am assuming that u1 is not equal to 0. So whatever number I am writing here, that particular thing is not equal to 0 is my assumption. So then I'll have only two equations, right? 4500 minus 10x1 minus 16x2 equal to 0. So for case A, the equations I'm solving are 10x1 plus 16x2 equal to 4500 and 9x1 plus 7x2 equal to 2500. So I just have two equations and two unknowns. So I can find x1 and x2 from here. So those are these x1 and x2. Once I get x1 and x2, how do I find u1 and u2? I'll go to the previous equation. So I have these equations again. So for example, I've taken 4 and 5. So once I take case A, I got x1 and x2 from here. And 6 and 7 I have not taken, which means u3 equal to 0, u4 equal to 0. That is what I'm assuming, because see, you can see like x1 is something that is not equal to 210 minus 2. So this is not 0, so u3 has to be 0. Again, x2 is not 230, so this is not equal to 0, which means u4 equal to 0. So I got u3, u4, I got x1 and x2. So once I got u3 and u4, I can substitute it here. This will be in terms of two equations, u1 and u2, u1 and u2. Two equations, two unknowns. I can solve this and get u1 and u2 values. So those are these u1 and u2 values. Yeah. You have to do that for all possible cases. But you can see the challenge here. You have to, how many number of equations you have to solve. This is exactly the problem, even in when you have cutting plane method or any of the methods that we have seen. So this is exactly the one that is solved using interior point method. If you would have used interior point method or something, where all these complementary slackness conditions are put in one big matrix and then you iteratively solve it. So what you do in this iterations is, instead of solving all the edge cases like I have done here, so I take different combinations. Here I've taken u1, u2 not equal to. So basically here I've taken u3, u4 equal to 0. So you can see I've assumed this to be two of them to be 0. Everywhere there will be two of them to be 0. So I've tried different combinations. So which combination will work is something that I do not know before, but these are all the edge cases that we want to refer to. So these are basically your extreme points. So instead of solving all these edge cases, I interior point method will actually go circumvent this in some other way. I have not done that here, but you can see later once after the course you can try it yourself. So once you solve it, these are the values of x1 and x2 and this objective function that you are getting. But you can understand the complexity, right? Till that part it should be clear. Yeah, time consuming process. But all of there, till now we have only linear problems, but you can also solve nonlinear problems. Now you can see how it becomes even more complicated when you have a nonlinear problem. Once you have a nonlinear problem with both equality and inequality constraint, then it becomes even more complicated. Now, for example, if I want to write the equations for this has three variables x1 and x2, one equality and one inequality constraint. So if I write the Lagrange for this, it will become something like this is my objective function, this is my equality constraint, this is my inequality constraint, and then I also have the extra constraint that x1, x2, x3 should be greater than or equal to 0. Those will be my extra constraints, okay, minus u3, x3. Now I have to have this big equation. Yes. Yeah, I show that as well. I have one more problem on that where I show you how to get these equations also. Let's say for now, for this problem, let's say you have the equations, then you have to just solve them. So you have to just put gradient of L to be 0, and this is my equality, and these are my complementary slackness conditions. Now you have around 8 or 9 equations, and you have to solve all of them with all these variables. So you have 3 variables here, 3 u's and 7 variables, and then you have how many equations? 9 equations. I think something I missed. Essentially, the number of equations and unknowns should be equal. So you have 4 plus 3, 7 equations and 7 unknowns. So you have to solve all of these equations simultaneously. That is a bit tedious one, but you will be able to do it. This is as a, if you want to do it with hand, after many trial and error, this is a very simple way I can write it down. You can go through it once you are done. But I think you got the idea. The idea is to write all these equations correctly and then solve them. But as coming to your question, how do we get that? For example, let's say this problem where you have a spherical reactor of some particular diameter d, and then the temperature of that particular fluid inside that reactor is T, and the fluid temperature is ambient temperature is T. You know the convective heat transfer coefficient as H. If, for example, the delta T is given by theta, and the heat transfer coefficient, you refer to some correlation books and you get the heat transfer coefficient. So this is my heat transfer coefficient. And if you recollect your strength of materials or some other course, you will always have the thickness versus, this is basically the temperature constant, which says that as you increase your temperature, the amount of diameter that material can withstand can also change. So whatever be the diameter that you take times the theta is some particular constant. This you cannot violate. This is like some constraint that you cannot violate. This is some correlation that you are getting from your tables. Now your optimization problem is to essentially minimize the net heat transfer from the sphere. For example, the spherical reactor, you are storing some material inside so that you don't, the material has to be maintained at a constant temperature. So you don't want a heat loss from the sphere. So what should be the optimal value of, so what are my decision variables here? So I'm trying to vary this, I need to find this d and theta that will actually like what temperature I can maintain and what diameter I can keep so that the heat transfer, heat loss from that reactor will be minimized. So these are my constraints. So if you put it mathematically, first thing is you write the equation for what your heat transfer is. So my heat transfer is the HA delta T, HA theta, where A is pi d square. So your Q is my objective function, which is this particular one, H pi d square theta. You can solve it as an unconstrained problem. So this is where you're writing. So what is my problem? Sorry. So if I write it in our form, so what we are trying to do is minimize Q is basically H pi d square theta. I am trying to change d and theta such that what are my constraints? My constraint is d theta equal to 75, where this H is given by the expression 2 plus. So this is my problem, right? Is clear? So now once I have it, now you have to solve it somehow. So one way to solve it is, now this is a, you can always use the implicit function theorem. So this is an two variable problem and it is constrained. So all I can do is, okay, take this theta as like, take this d here, make this entire problem in a function of, uh, get theta as a function of d, substitute it in the original equation, make the entire problem in terms of d. So it will be single variable problem. So then it is an unconstrained problem. So I can just take d to d equal to 0, and that will give me the value of q. So that is a very simple one. So you can substitute, get the value of d, and then you can back substitute theta, get the value of theta, and once you have d and theta, you can substitute in your q and get the value of q. The other way to solve it is using a constraint problem, where you write it in using your Lagrange function. So this is my objective function plus lambda times your constraint. and you try to make the gradient of this L equal to 0. Then you have del L del D equal to 0, del L del theta, and d theta equal to 75. So you have three equations and you have three unknowns, d, theta, and lambda. So now you have to solve these three equations. Again, these are nonlinear equations, so you have to find some way to solve them. So you can use Newton's method or any other method that we have discussed, line search or any method, and solve these three equations somehow. So, but here it is a very simple one, so you can directly substitute and get your solution. You solve for lambda, make lambda in terms of d, substitute it back, then you have equation for d, which you can solve using some root solving and get the value of d. Once you have d, you can substitute it back to get theta, lambda, and q. But is this part clear? I think this is what you asked, right? How do we get these equations? How do we get this d theta or something? Yeah, or you have to get your own equation. So, for example, if you are solving some fluid dynamics problem or say transfer problem, these are the usually the. For example, if you have let's say you want to design a car or something, there will be some standards that will tell you, okay, this should be the minimum height that you have to meet. For example, if you are designing an air conditioning system or something, some ducting system or something, you know that there is a certain amount of noise level that you have to maintain. There are some standards that says you need to have this much access space in case of some maintenance or something. So your duct diameter cannot be smaller than this. There will also be constraint which says the amount of flow rate inside the duct cannot be greater than this because that will cause more noise or something. All those things have to be put in. So those constraints will come from the domain expertise. So whoever is in that domain, whatever the problem you are solving, that particular domain expert will tell you what the constraints are. All the thing that you have to do is formulate them mathematically in a way so that again we discuss like how do we get these equations. I can sell the same thing in different ways. I can say that the noise level should not be greater than so and so, but then I can how to get the noise level. The same equation can be written in 100 different ways. That's exactly where we discussed on the constraint qualification theorem. So you have to come up with some equations such that all those equations are linearly independent or in some way. So your constraint qualification should hold. Only then you can put them and solve a problem. Otherwise, it will be most of them will be redundant, and you have to use some other method to identify. Okay, these are redundant, so I have to reduce the number of constraints. And those are other post-processing things that you have to do. Yeah, but the basics are the same. So all these questions are taken from a course in our college, IIT Madras by C. Balaji. The course is also available on NPTEL, I guess. You can go through that as well if you want. But most of them are focused only on mechanical energy system, mechanical systems. Examples are the mechanical systems. Okay, and these examples, so the questions that I discussed here are taken from his textbook only. Some of them are solved examples and some of them are exercises at the back of the book. Yeah. Are there any questions? Yeah. Yeah, this is the kind of some material consideration that has been. So some from some tables. It's like an expert thing. And theta is the temperature. It's basically as your temperature increases, then the material thickness cannot be more than so and so limit or something like that. So if theta, so you can think of this like if you keep on increasing the diameter, then the total area will increase. So your heat transfer will increase. So it's like if you have a very big reactor, then your total area is increased. So it will also increase. But then the problem is as your D increases, the amount of theta is basically the difference between the whatever inside the reactor and whatever the ambient. The amount of that difference you cannot maintain properly. So you can have as D increases, your theta will become small and small. But I don't want theta to become small. I want theta to be I need theta to be as high as possible. It's like okay, if I have a reactor maintaining temperature 25 degrees Celsius, say I have a tank and I'm maintaining some say liquid nitrogen. Sorry, I maintain some fluid inside the tank, and that whatever fluid inside the tank is say 20 degrees Celsius and outside is also 20 degrees Celsius, then there is no point of the tank, right? I need whatever inside the tank should be at some finite value of theta. Like it should be some 10 degrees Celsius lower, or for example, if I have a liquid nitrogen, it is say minus 77 or something, whatever the temperature is. Say it's like a refrigerator where you are, if the inside temperature of refrigerator is same as outside temperature, then theta is 0. Then there is no point in having that refrigerator. So that is exactly this thing. So you can have a very big container, but as you keep increasing the container, the ability to maintain the theta will keep decreasing because of increased heat transfer. So I have to increase theta. At the same time, I also have to increase my T, but I cannot do both of them simultaneously. So there is a trade-off between. So how much weightage should I give for T and how much weightage should I give for theta? That is something that is given by this equation. So it is say that okay, you can increase this so much, but if you keep increasing T, your theta will proportionally decrease so that this product is a constant. This is one way of writing the equation. You can have multiple ways of writing the same equation. Yeah, it becomes a, yeah, it is taken in this example problem, it is taken, but if you are in your research problem, you have to make those constraints yourself. Yes. And then you might also encounter a different problem wherein say you have an equality constraint. The equality constraints are actually straightforward. So they are equality, so it is an equality, so there is no problem. But the inequality constraints are the real problem. So whenever you have an inequality constraint, something less than or equal to 0 or less than or equal to some standard set point. If it is already available, you take from the standards. If it is not available, then you might have to do some experiments to get those values, get these values of 2.5 and so on. So like for example, in your, if no one has done before for a spherical reactor, then you have to do your own set of experiments with different values of B, different values of theta, and then you have to use the curve fitting. Say you will formulate this something as h equal to some a plus, sorry, what happened? Yeah, so we'll write it as a plus b times theta power m d power n or something, and then you have to find this a, b, m, and n from your data. So essentially, you'll do something like h minus a equal to b times theta power n d power n. Apply some log or something. Once you have this data, you fit a linear regression that we discussed in this course. Then you'll get these values, m, n, ln p, and all these values. But this a is something that you have to figure out in some other way. Then once you have these values, from there you can get this h. But then you might not always have to do experiments. Someone would have already done it and they would have already given it, so you can use it. But if no one has done it, if it is a new scenario that you are doing, then you have to get these equations yourself. Any other questions? And maybe for you it might be useful later. You might have to. Uh, I don't know if you're familiar with multi-objective problems. Like all the problems that we discussed in this lecture have basically one objective, single objective, right? You try to minimize some function. That is the only problem. But then mostly what will happen is when you in your research you might find scenarios where you have to minimize two, three functions. So those are called the multi-objective problems. So those are another thing. There are different methods for that as well. So again, there also use the penalty function again in a way to determine how much weightage to give for each objective and then convert a multi-objective to a single objective problem and then solve it. That is one way of doing it, but then that is not the only way. You can also solve it using some other methods. There is one course in NPTEL on multi-objective optimization as well. You can also go through that. Yeah, but I do not remember the exact name, but it goes with multi-objective optimization. You can also see on my YouTube channel. But the one that I have discussed is on multi-objective, but then using evolutionary computation methods. So the methods here that we are discussing are gradient-based methods, right? Most often or not, you use some gradient, gradient or something. But then the only problem is you cannot always find the gradient of a function. If the function is not continuous, then you cannot use it. So you have to use some other methods. This course, we told you only the fundamentals where you know that solution exists and how to go about it. But we spent very little time on how to actually use it, on the methods to use to solve it. The only methods that we discussed are line search, Newton's method. These are widely used methods, Newton's method or interior programming and all these methods. But then our functions are analytical functions. They are some kind of continuous functions and stuff. But you might encounter scenarios where the functions are not continuous, not differentiable. Then you cannot use these techniques directly. Discrete, as in, you can use interior programming techniques. You can use some, like if it is an integer problem or something, or is something else. But discrete, I think there are different techniques. For, there in integer programming and other stuff there were there, right? I haven't done the discrete one. Discrete is a different thing. So your continuity is also not satisfied, right? Yeah, I have not dealt with such problems. But the problems I usually encounter are the functions are continuous but not differentiable. And usually the problem is calculating the gradient itself is difficult. So, for example, consider this scenario: you are solving a CFD problem. Let's say you use some ANSYS simulation or something. So you take some velocity condition. You want to identify there is, for example, if you're trying to simulate a room. So there are some occupants inside the room. You want to decide how much velocity you have to send the air from the diffuser. So now the question is, the objective function is the thermal comfort of the occupants. So how do I get the derivative of that with respect to the inlet velocity? There are some techniques to do that, but then usually it will be a little difficult. So you don't even have to worry about it. It is a continuous function, that is for sure. For every velocity, I'll have some unique value of this temperature, and then it will become continuous and all of that. But then calculating the derivative is a difficult thing because I do not know the analytical function. So then these techniques like evolutionary computation is where it become useful, and it will also become useful when you can actually do this in multiple cores and stuff like computation. Now it is possible. Previously it wasn't, but now it is possible to do all this. And coding the evolutionary thing is also very easy. But the only challenge is the number of parameters you are going to have. There are so many parameters, and you identifying the right parameters is actually difficult. But then those are some techniques that are actually used even in the literature. You can refer that as well. Yeah, but that's it from my side. If you have any other further questions, we can discuss. Otherwise, we can end the session. Yeah, sure. Hope you like the class. And you are appearing for exam, so best of luck for your exam. Okay, then we'll conclude this. Yeah, this is the last session for this week. Sorry, not for this week, for this particular course. No, this is the last session for this particular course. So if you have any further queries, you can post it on the discussion forum as well, like regarding the exam or something, because I'm not familiar with the exam patterns and stuff. So anything regarding exam or any administrative things, how to get your hall tickets, how to go to the center and all the stuff, where then the center will be allocated, or any of the administrative things that you have, you can post it in the discussion forum. The NPTEL team will respond to that. Okay. Okay. We'll have the session for today. Thank you.